we introduce a new realistic synthetic dataset called AGORA that addresses limitations of previous datasets, reveals failure modes of existing methods, and even leads to better performance on in-the-wild datasets. AGORA uses commercially available high-quality textured 3D scans from Render People, Human Alloy, 3D People, and Axis Design, with varied pose, clothing, and identity. To each scan, we precisely fit a SMPL-X body model to provide ground truth 3D body pose, hand pose, and facial expressions. Given multiple scans of the same person, our method considers semantic, geometric, and subject identity information to estimate their SMPL-X parameters. The reconstructed SMPL-X fits yield, on average, 5 millimeters of shape error. Next, we render up to 15 scans in a realistic scene with random variations in orientation, number of subjects, intersubject distance, and distances to the camera. We use a mix of high dynamic range images in which people are placed on a ground plane and synthetic 3D scenes that provide environmental occlusion. We render around 14,000 training and 3,000 test images. We provide the training images with ground truth SMPL-X and simple bodies, as well as 2D segmentation masks. We provide test images without ground truth data, but with evaluation code and a web-based evaluation server. AGORA provides a challenging evaluation dataset to test current methods, but it also provides training data to improve them. For example, we use the AGORA training set to fine-tune spin. We find that despite being synthetic, fine-tuning on AGORA improves the performance of spin on 3D PW, a natural image dataset. We have presented AGORA, a new dataset to advance the field of 3D human pose and shape estimation. Future work includes better integrating the observed probability to the robust loss function and using photometric loss to further improve the registration.
AMASS is a large and varied database of moving human bodies that unifies different optical marker-based motion capture or mocap datasets by representing them within a common framework and parameterization. Large datasets are the cornerstone of recent advances in data-driven learning-based computer vision and computer graphic methods. However, existing human motion datasets are small and limited, hence hampering such data-oriented methods on human motion data. While there exist many different individual high-quality mocap datasets, they each use a different parameterization of the body, making it difficult to integrate them into a single metadataset. AMASS addresses this issue by using a new method, MOSH++, to accurately convert labeled mocap data into realistic 3D human meshes represented by a rigged body model. AMASS uses SMPL, which is a widely used body model, providing a standard skeletal representation as well as a fully rigged surface mesh, including soft tissue dynamics and realistic hand motion. SMPL is differentiable, hence can be used as any other layer in a learning-based algorithm. The consistent representation of AMASS makes it readily useful for animation, visualization, and generating training data for deep learning. AMASS is significantly richer than previous human motion collections, having more than 48 hours of motion data, spanning over 450 subjects and more than 14,000 motions. AMASS is constantly growing, so if you have mocap data that you want to share with the community, we can process it with MOSH++. The mocap data could either be labeled and cleaned or even raw and unlabeled.
Learning semantic representations of the 3D human movement is an important problem. For tasks like action synthesis or action recognition with natural human movements, it is critical to have high-quality 3D movement data where each frame is labeled with all the actions that are happening. We address these shortcomings with BABEL, a large-scale dataset with dense action annotations for ground truth 3D human movement that are derived from the AMASS dataset. Each action label in BABEL is precisely aligned with the frames depicting the action. This includes simultaneous actions and transitions between actions. To label these actions, we recruit annotators from Amazon Mechanical Turk. They first watch the video, enter all the actions in the movement, and then align the span of the action label with the duration of the action in the video. We ensure that every frame of the sequence is annotated. Here's an example of an everyday activity: listening to music. BABEL captures the simultaneous actions like looking around while holding the device with the left hand while adjusting the settings with the right hand. Given the long tail distribution of actions that resemble real world data, we believe that BABEL will serve as a good benchmark for tasks like action recognition, action synthesis, temporal action localization, etc. The BABEL dataset splits, baseline models, and evaluation code are publicly available at our project webpage. Thank you.
We collected BUFF, Bodies Under Flowing Fashion, a novel dataset of high-quality 4D scans of people in clothing. BUFF includes 3 males, 3 females, 2 clothing styles, and 3 motions, totaling more than 13,600 scans. We also computed the ground truth shapes in minimal clothing for every subject from motion sequences like the one shown here. The estimated shape in a T-pose is shown in white. The dataset includes ground shapes for every subject in the dataset. Examples for 5 of the subjects are shown here. Such ground truth shapes will only be used to validate the accuracy of different methods for shape estimation. The released scans also include dynamic textures as shown here.
Hi, I'm Qianli, and this is a CAPE dataset, a large-scale dataset of dynamic 3D humans in clothing. It provides registered meshes from real 4D scans of clothed humans, performing a variety of motion sequences. The dataset includes 15 subjects, with in total 41 unique outfits, performing overall more than 600 motion sequences. For each frame, we provide the simple pose parameters and meshes in both the posed space, as shown here in the top, and the canonical T-pose, as shown in the bottom. Apart from these, for each subject, we also provide the ground truth minimally closed body shapes that are registered from accurate scans as well. Moreover, upon request, we also provide the valuable high-resolution raw scans of the closed humans. The CAPE dataset can be used in many different ways. For example, to learn generative models of humans in clothing, as done in the original CAPE paper, to learn non-rigid mesh registration, to train models of pose-dependent 3D shapes of neural avatars, as done in several pieces of recent work, and many more. Comparing to other static or rigged dataset of clothed humans, the CAPE dataset is special not only in this great pose variation, but that the clothing shape varies with the body pose. This makes the dataset especially suitable for learning non-rigid articulated shapes, such as pose-dependent clothing deformation that's essential for creating realistic avatars. Finally, a small tip. If you are already using the CAPE dataset and notice some distortions on the subject's feet or fingers in your results, it's probably not a problem with your method, but the imperfection in the dataset. We noticed that too, and we'll release a fix for that soon. That's it. Please check our website for more information. Thank you.
The COMA dataset is a dynamic 3D face dataset of extreme and asymmetric facial expressions. The dataset contains sequences of 12 subjects performing different expressions. For each subject, the dataset contains 12 sequences. For each frame, the dataset contains 6 raw RGB camera images, a 3D face scan with about 120,000 vertices, and a registered mesh and flame topology. The registered meshes have been used in several other works to evaluate different mesh convolution architectures. The COMA dataset consists of 144 sequences with in total more than 20,000 frames.
Hello everyone, I'm happy to share with you 2 MU datasets, synthetic AMASS and DIP-MU. For synthetic AMASS, we ran MOSH to turn archival mocap markers into simple body mesh, then place virtual MUs on the body parts to get orientation and accelerations. For DIP-MU, we place 17 MUs on the major body parts, then feed simple into the MU regions. Synthetic AMASS is the biggest MU dataset so far, and DIP-MU is twice the size of total capture, a previous real MU dataset. Some samples of DIP-MU are shown here. to give you a rough idea of how the data looks like. These two are mainly used in body pose estimation from AMASS, like showing differential pose and transpose. They can also be used in other areas like activity recognition and biological study of human motion. This demo shows what is achieved in differential pose. The person is being tracked from 6 AMASS faithfully in real time. For more information about the data, please go to our website. Thanks for your attention.
A key goal of computer vision is to estimate human-object interactions from video. The way humans interact with objects is important to understand human goals and behavior. Learning models of human-object interaction requires data. To this end, we present a new database called GRAB of people interacting with objects. GRAB captures the full 3D human body, hands, and face in more detail than any previous dataset. To capture whole body grasps, we fit an expressive 3D model to motion capture data. Capturing human-object interaction also requires accurate 3D object models. For this reason, we 3D print the objects from the CONTACT-DB database. To capture their motion precisely, we glue small hemispherical reflective markers to their surface. Simplex represents the surface of the human body. This enables us to infer the contact between the human and the object surface. Contact regions on the object are shown in red and are enlarged for visibility. Aggregating contact maps over time gives contact heat maps on both the human and object surface. GRAB contains 10 subjects interacting with 51 everyday objects of various shapes and sizes. The GRAB dataset goes significantly beyond any previous dataset for modeling and understanding object grasping and manipulation. In total, it includes more than 1,300 sequences and 1.6 million frames. GRAB is designed for machine learning. We use GRAB to train GrabNet, a novel conditional generative network to predict 3D grasps of unseen objects. Here, we focus only on the hand and extract mano-hand parameters from the simplex body. By inferring parameters of the mano-hand model, GrabNet constrains contact to be anthropomorphically plausible. Here, we see generated grasps for several unseen object shapes. To facilitate research in these directions, the GRAB dataset and GrabNet model are available for research purposes. Please visit our project website for more details.
Existing 3D pose estimation datasets are collected in indoor and restricted environments. 3DPW is the first dataset collected for in-the-wild images. 3DPW makes use of IMUs worn on the limbs of a target person and an external handheld camera. Here we show some of the image sequences in the 3DPW dataset. In conjunction with the ECCB 2020, Gerard Ponsmall, Anju Kanazawa, Michael Black, and Ayman Mir organized the first 3D-PW challenge, which makes use of the entire 3D-PW dataset. The aim of the challenge was to establish new benchmarks and metrics for evaluating 3D pose estimation algorithms. The evaluation code for the challenge is available online.
Serial is a synthetic dataset, meaning artificially generated, and the goal is to generate synthetic but photorealistic videos of people for training data-hungry deep neural networks. This data contains 60,000 videos, each with about 100 frames. To do this, we use a graphics engine, Blender, together with several assets. This work has become possible thanks to the flexible simple body model that now supports a variety of platforms. When creating one video in the Serial dataset, a 3D body with random 3D shape is configured in a random pose, and a synthetic image is rendered by randomly sampling a camera, lighting, clothing texture, and a static background image. Together with the RGB frame, pose, surface normals, optical flow, depth, and segmentation are generated. While the videos are purely synthetic, the assets we use are from real data as an effort to reduce the domain gap as much as possible. To showcase the benefits of synthetic data, we trained convolutional neural network models on these images and demonstrate their generalization capability on real test samples, in this case for body part segmentation and depth estimation tasks. Synthetic training especially helps when there is no sufficient real data. We show that pre-training on synthetic and fine-tuning on real consistently improves the segmentation performance over training only on real. Since this work, a number of follow-up works appeared addressing a variety of other tasks using synthetic training. You can also make use of our synthetic data generation code as well as the rendered images by checking our webpage. Thank you for listening.
Welcome, I'm Leah, and I'm excited to show you 3 new datasets that we published with our Touch project at this year's CVPR. First, we have 3DCP scan, which has 500 scans of 6 subjects in various self-contact poses. You have not seen these poses in publicly available datasets before, I promise. And we have high-quality registrations in SMPL-X topology for each scan. Then we have MTP, a dataset of 3.7K in the wild images with accurate 3D reference poses. For this, we ask 148 workers on Amazon Mechanical Turk to mimic self-contact poses. And then we use the presented pose and contact and the ground truth height, weight, and gender to fit the SMPL-X mesh to the mimicked images. And these fits are so good that we use them in touch training as if they were ground truth. Last but not least, we have discrete self-contact annotations for 3 publicly available datasets. To create them, we divide the mesh into 24 regions and annotate their pairwise contact. These annotations can be used with Simplify or Simplify-X.
VOCA set is a dynamic phase dataset with 29 minutes of 40 scans with synchronized audio. The dataset contains sequences of 12 subjects.
Are those shy Eurasian footwear, cowboy chaps, or jolly earth-moving headgear? Don't ask me to carry an oily rag like that.
Pledge to participate in Nevada's aquatic competition.
Each subject speaks 40 English sentences of length 3 to 5 seconds.
Iris thinks this zoo has 11 Spanish zebras. Cement is measured in cubic yards. How many clubs, projects, and societies is the union responsible for managing?
The dataset contains calibrated raw scanner RGB images, raw 3D scans with about 120,000 vertices, registered meshes in FLAME topology, and unpaused registered meshes where effects of global rotation, translation, and head rotation around the neck are removed.
Are those shy Eurasian footwear, cowboy chaps, or jolly earth-moving headgear?
The data can be used to train a voice-operated 3D character animation where the speech signal is used to animate a 3D face mesh. VOCA set consists of 480 sequences of 270 unique English sentences.